So the first part of this problem is actually quite simple. It really refers to going back to the picture of the ball traveling around in a circle like so. And you take a look at this and you say, what is the first thing I should do anytime that I run into an object that is in circular motion? Force diagram. The minute you draw a force diagram for this object, you will realize that this problem can be easily solved. So the force diagram is as follows. The first one is a good old Ft that is pointing in the direction of the rope. So that Ft drops in there. And then, of course, there is an Fg component of the earth pulling down. Now, the other thing that you should always think about, you have an object in circular motion. That means you know the acceleration of that object at that point. And we know that the acceleration must be pointing towards the center of the circle at that moment. So that means there must be a net force going to the left at this point. So the moment I look at my force diagram, I'm like, what could actually be my force going to the left? And you'll see that any force that's at an angle, we should break up into the Ftx component and the Fty component. The moment you do that, you realize that the Fty is equal to Fg. Oh, that's so nice because, well, we already know one of the legs of the triangle here. And again, our goal, I'm going to try to be fancy here. Our goal is to solve for that guy right there, the Ft. And we know one of the legs, which is awesome. Now, the other question is, how do we get the other leg? How do we get Ftx? And that's going to be kind of the big idea in here. How to get Ftx? Well, this is where circular motion comes into play, because you notice that Ftx is the net force, it is the centripetal force, it is the force that is causing the acceleration. So the moment I say that, I should probably write it out. Net force is equal to Ftx. So that's a big statement here. And as always, after you write down net force equals Ftx, you should write down it is the same as mass times acceleration. That is our equation for that. Now, I look at that equation, mass times acceleration. Life is good. I know the mass. Now, to get the acceleration. And the new idea in this unit is this is the centripetal acceleration, which means I can go back and say, hey, AC, what is going on? AC is equal to V squared over R. So you get V squared over R. You notice, hey, I know the radius. Is there a way to solve for the velocity? Yes, there is. The good old V equals 2 pi R over T. And we can go plug in there. You realize that you know the radius and you know the time it takes to do that, so you actually know the V. And once you know the V, holy cow, everything is starting to become a smiley face, and you realize that you actually know the acceleration there as well. So you get the acceleration. Maybe you get even happier here. Maybe, yes, I have this. Oh, that's a horrible smiley face, but that's okay. We have that, and you realize that now you know the Ftx. Maybe this is the smiley face that I was looking for. A little bit better than the other one. But now you know the Ftx, which means we go back on over here. And once you know two sides of the triangle, you're good to go. Through our good old a squared plus b squared equals c squared, or Fty squared plus Ftx squared is equal to Ft squared. So I think dependent on the quiz that you got, if your radius was 1 meter, I believe it was 5.37 is your answer there. If your radius was 2 meters, your answer is 6.57. Is it roughly? It's crazy that I still remember that, but yes, those are the two values that go along with that. So,